Hi, my name is Leandro Facchinetti, and let's write some code together, shall we? What we have on the menu today is the third part of this series about RMS. And in this part, we are going to talk about yet another way to compute RMS that is not the definitional one from the first video, and it's not the optimization from the second video. It is even more optimized than that. Because in either one of the previous videos, we had to keep track of a bunch of samples. We had to keep a window of samples. And while that is good, because if you're doing it in the way that we did in the previous video, it is fast enough, it's kind of annoying to have to keep this window around and update the circular buffer. Also, it is slightly less performance than the way we are going to do in this video. But the trade-off is that the way that we're going to do in this video kind of loses some information. And it's not a perfect optimization, it is an approximation of the RMS. But it's still useful in many contexts. Maybe if you have a compressor, you wouldn't even be able to hear the difference if you're computing RMS in one way or the other. So let's dive into this. The idea is pretty simple, actually, and it kind of relates to similar ideas in the fields of economics and in the fields of biology. I don't know. It has relationships to other ideas in other fields. So what we were doing before is we had this window of samples, or in the second video, the previous video, we had a window of the squares of the samples. And when a new sample comes in, we update this window in time. We move it forward. So if you think of the axis of time, what we are doing is we have this window moving over the time. And I think there are some other names for this, like boxcar, because it kind of looks like a boxcar, a window moving over time, or a rectangular window. There are all these sorts of names for this idea. What we are doing today is a different kind of window. It's not a rectangular window. What we effectively want to do is to get rid of having to store all the samples from the past, or at least some samples from the past up to some window size. What we want is to just have a single variable that is going to keep track of the sum, and then we can take the square root and the average, and then we get the RMS value. So the way we are doing this in this video is, let's move on to the computer, and I'll draw here some ideas for us to think about. So suppose that you have some samples coming in and they draw a shape that look like this. Don't know what that was about. Anyway, they draw a shape like this. So these are the samples, the sound pressure, or the position of the speaker cone in time. And then the boxcar approximation, the rectangular window, the thing we were doing before would keep track of this much samples, and then another sample would come in and it would update the window like so. That's something that is conceptually simple, and that's what we have been doing. But suppose that instead, what we did is we just we drew a similar line to this one, but it would smooth the fast differences. So another way to think about this is as if this was a low-pass filter, and we are going to talk more about filters in some future video. But the idea here is that we are going to move along with this line, but we are not going to react as fast as this line does, which is more or less in line with the idea we began with, which was RMS is a way for us to look at the levels that is slightly more reliable than peak meters, because it doesn't react as fast to changes over time. So it correlates better with the way that we perceive sound. So we are going to move along with this line. So when this line is going up, we are going up, but we are not going up as fast. So we are moving up like this. And then the other line is moving down. We start to move down as well, but we don't move as fast. And then there is this spike that I'm going over right now here on the bottom, and I don't simulate what the spike is doing. I just move along more slowly. And then it starts to pick up again, and I pick up again, but not as fast and not as drastically. This is more or less what the RMS meter is going to show over time anyway. It's going to react to changes, but not as fast. And some of the changes that are very fast, well, we just don't see them at all, or we see them much more attenuated here on RMS. This is the idea of a moving average. That's the name of this concept. It's a moving average. Because we are averaging the previous values, if it's going up, then we are going up. So we are sensitive to previous values, but it is an average. We are not sensitive to very sharp changes. So that's what we are going to do in this video. We are going to do this moving average, and we're going to do the moving average not of the samples, but of the squares of the samples, because then we are already halfway through the computation of RMS. If we have the squares, if we have an average of the squares, then we can just divide, we can just take the square root and we have the RMS computation. We don't have to do any division here because the moving average is already going to do the division for us. Okay, so that is the idea of the moving average. Let's go over to our code and see how we can start implementing this. Okay, so this is the code as we left it. And for sure, what I want to do is to start with, I want another slider, which will be the RMS in dB. And this time, I'm tempted to call this approximated, because this is the definition, this is optimized. This is approximated. We are now computing RMS with this other concept that is an approximation. So we still want to have the same range, but the label is going to read approximated. And I will also want to initialize the running average, the moving average. I also want to initialize it similar to what we are doing here and here. But as I said, we don't need the window. We just need the running sum. So here we had the running sum. This was actually the window. That's not what we want. We don't have a window anymore. In fact, I'm going to move. I was thinking maybe I can define this variable here on the bottom of this free mbuff to make sure that it is clear that we don't have really a window here. We just have the well, I'm going to follow the convention and leave approximated as the suffix for all the variables. We have here a moving average approximated. And it's going to be a moving average of the squares of the samples. But I'm not going to put that in the variable name because it would be just too long. Also, I don't want to have necessarily the window pointer after this. I want to have the window pointer before this because this is a different topic. So now we have here on every sample, we are going to do some work. And the work is for our approximated version. And we want to update this moving average approximated. We want to do something to it. Well, what we want to do is to move that moving average, this line here, we want to move it closer to the current sample. We don't want to move it to the current sample. Let's just move it to the current sample to begin with. That's a way to move that average to the current sample. And I'm going to start with this just because I want to write the rest of the logic for this, but we'll get back to this because this is definitely incorrect. So the moving average approximated is incorrect because it's moving to the sample. So it's following this line that is the line of the samples precisely. And no, we want to move more slowly. Anyway, let's start with this. And then we also need to do this part, which is similar. Let's see. The RMS amplitude approximated is the square root of the moving average approximated. And this time, as I said before, we don't need to divide by the number of samples. We don't need to divide by the window size because our moving average idea here, we already have the division. It will be baked into the way we are computing this. No need to divide this. So we just take the square root and we have the RMS amplitude approximated, and then we do the conversion to dB, and that's what we show. So I'm going to just rename some of the variables here, and we'll have done the whole steps except for this part, which is the main topic of this video. Also, we want to update slider 5 now, because that's the slider that is showing the RMS dB approximated. Now let's save these, and I'll put this on the side just so we can look at what this is giving us. Okay, so we can tell that RMS, definitional, and optimized are moving along together because they are computing the same value, but this is reacting very fast to the way the samples are going. In fact, there is already a problem with this, and that is we are not taking the square of the sample. So I definitely want to take the square of the sample. Okay, but it's still moving erratically, maybe even more so now that I'm taking the square of the sample. We want this to move more slowly. We want to move along, but way more slowly. Okay, how can we do this? Well, we can add up the difference between our current value and whatever is coming in. And as you can tell, this computation that I'm doing here is not really doing much, because what I'm doing is, let's say, how about we do it like this? Yeah, so I definitely am not doing anything here because I just am adding and subtracting myself, the moving average approximated. But we can rewrite this like so. This is adding, this is subtracting, so it comes here. Like so, yes. So this is another way of writing that. I am not doing anything different here because I am still adding and subtracting myself. And in effect, I am just moving along with this line. I am not moving more slowly. Well, how can I move more slowly? What this is giving us, and that's why I wanted to write it this way, I wanted to write the formula this way, is it's giving us a difference between where we would like to be, and that is, for instance, in this case, this line at this point right here. This is where I would like to be. This is the sample coming in. So my moving average needs to move toward here. That's where I would like to be. I want to seek this point. So by adding this, I am seeking this point, and of course, I want to subtract where I am. So what I'm doing here is just moving toward that point. Another way of seeing this is that we are, for instance, here, and another sample comes in, and it's up there. So what we do is we add the sample and subtract ourselves, so we don't end up here. We want to move closer to here. And right now, what we are doing is we are moving super fast to here because we are moving along with this line as fast as this line is moving. Well, how can we change this? How can we move more slowly? Well, we want to move toward the sample, but what if we multiply this by some value that is between 0 and 1? If it's 1, then it looks like this. And we are still moving very fast. We are moving towards, actually what I want to do in terms of window management is put this here and put this there. Now we can see the meters moving along with the code that we are writing. So now what we are doing is still the same, but if we change this value to something like 0.5, then this starts to move more slowly. And if it's 0.1, it moves more slowly still. And if it's 0.001, then it starts to move very slowly. As you can see, we are moving toward the RMS. When I speak, it comes up. When I stop speaking, it goes down. It's now just a matter of figuring out what is the right coefficient here. What is the number that I need to put here so that we are computing the RMS for the given window size, or at least we are approximating that window size. This is an approximation, because if you think about it, I am never zeroing the moving average approximated. I'm never saying, okay, now reset, go back to some known value. For instance, here, 0 was the beginning of the moving average approximated. Or I could maybe, because this is an approximation, from time to time, I could just zero it and maybe have a window just to reset this. I don't know. I don't have any of this. All I'm doing is just adding more and more and more information to this moving average approximated. On every sample, I am adding up some value. So I'm never discarding whatever was there. So everything I said up to this point, since I saved this file and this RMS approximated started to compute, everything I said is still in some small shape affecting the current computation. But the thing is, every time we go through another sample, we are multiplying the previous value by a very small number. So eventually, things in the past begin to not matter that much anymore. The contribution they have is negligible. The samples from the past are still contributing some, but very, very little. And the samples that are coming, the samples that are new, they have been multiplied by a small number fewer times. So think about it. The sample comes in and it's multiplied by this small number, yes, but then it is embedded because it has been added. So it's now in this number, and then it goes along on the next sample, it's here in this number, and the sample is multiplied by a small number again, and then again, and then again, and again. So as time moves on, the sample is still contributing, but it's contributing less and less and less. And in fact, because on every sample we are multiplying by a coefficient, it is contributing exponentially less over time. And the name of this idea is a moving average that is an exponentially weighted moving average, because we are multiplying this number again and again and again. And of course, as we are multiplying the same number again and again and again, another way of saying this is that we are, like, on the first time around, it is that number to the power of 1. The second time around, it's that number to the power of 2, and so on, because we are multiplying the same number again and again. So we are, in effect, doing this as the samples are coming in, because we are doing this in a loop. Okay, now let's think about this problem of how do I pick this coefficient so that it correlates more or less to the window size. Because I could just try to find a value here. If I changed this and I kept tweaking it, I could find a value that would make this slider move as fast as the other ones, or at least close enough that we could say that the approximation is good enough. Well, yes, that is one way of doing it. We could try to just pick a right value. But there is a way to correlate the window size and this coefficient. And this is the part where it gets really annoying, because I tried to find this in many places online, and I found on these forums, and everyone just kept saying, yeah, sure, what you need to do is just compute a one-pole low-pass filter of whatever. And I was like, what the hell is going on? Why don't you just explain this in simple terms? And even when people try to explain this idea of the moving average, they always said, yeah, and then you just pick a coefficient. And I was like, okay, but how do I pick one? Do I just tweak one? Do I just give the user a slider to find a coefficient? I would like to think in terms of milliseconds. How do I pick a window size in milliseconds and transform that into a coefficient? And I had to do a lot of searching to find this, but eventually I found something. And it seems like this is related to the half-life or decay of radioactive matter, and it also has to do with other things in economics and physics and biology. I don't know. It has a lot of connections here, but there is this way to compute a coefficient from a window size that gives the moving average a decay. So the contributions of the samples are decaying over time in a way that, so that when 300 milliseconds has passed, then the contribution of the sample will be about half as much, I think. I think that's how it relates to a half-life. So now what we are talking about is the half-life of a sample, or the square of a sample, really. The half-life of the thing we are computing the moving average of, which I think is a super crazy idea if you think about it. Anyway, so now let's talk about how we can compute this coefficient. And I will call this the moving average approximated coefficient. I think this is commonly called the decay or A and B, because people like to give these things excellent names like A and B. And I'm not going to try to make sense of how this formula that I'm about to write it comes about, because I don't fully understand how it works. But I definitely know that it's a correlation between the window size and how we want to calculate this coefficient. So we have the size in samples. So we definitely want to start with that, because we are talking about samples here when they're coming in. So I don't want to talk about in terms of milliseconds. I want to have this converted already, and I have. And then what I want to do is, and here comes the crazy part, I want to take e, the number e, to the power of 1 over the window size in samples. But not only that, I want to take the negative e to, or I want to take e to the negative 1 over the window size in samples. And then this number here is going to be close to 1, I think. Yes, this number is close to 1. So I want to take the opposite of that. So you can see that when I save this, you can see that this value is close to 0. It's a small number. The number we have here is a small number, and the number we have here is a small number. And we want small numbers because small numbers mean that our moving average is moving toward our goal more slowly. We want small numbers. If the numbers are close to 1, then we are moving to the sample here more rapidly. And if the number is greater than 1, then we are overshooting. So the sample is here, and our moving average comes from here to there. Overshooting. Definitely not what we want. We always want this number to be between 0 and 1. And of course, if it's 0, then there is the other extreme. We have to think about it. If it's 0, then the whole thing that we are multiplying, the coefficient is being used here, or at least it will be used here. So we are multiplying by 0 every time. So if this number is 0, then we are not moving. The moving average is just stagnated. Oh, come on, get out of the way. Okay, so the moving average just stays in place if this is 0. And if it's 1, then it moves. Let me close this one. Okay, so if it's 1, it's moving too fast. If it's a small number, it is moving more slowly. Now let's look at the approximation. So this is the coefficient approximated, the one we just looked at. And I think that it does kind of a good job, but it's not perfect. It is moving more or less in line with the others, but it decays a lot more slowly. And that is just something that I don't know. Maybe if I choose another coefficient, if I change this formula somehow. I saw, for instance, some people just multiplying by 4, and I have no idea where that comes from, but I saw some people doing that, and maybe if I multiply by 4, then it moves more, it moves faster. And now there is some bug here with RMS optimized, because it's resting in a different number. I have no idea what that is about. Anyway, the definitional one is moving more or less in line with ours, with the approximated. Yeah, when I stop speaking, it moves to the left more or less in line with this. I don't know why people multiply by 4 here, but one thing I know is I kind of dislike this approximation. I don't think it's a very good one. I saw some plugins using this. Like I said in the previous video, there is the Tri-Leveler by Sonic Anomaly, and you can check out their source code because it is open source. It's a JS effect. There is also the CWL plugins, And the original auto mixer, not the one I created, and you can see another video about this in this channel, but there is the original auto mixer, and it gives you an option to calculate RMS using this approximation. I cannot really make sense of this. I don't really like it, but it is an option. Yeah, I figured what the problem was with your RMS optimized. I had to do a full compile reset, so it was just junk. For some reason, there was some junk in there. And before I leave, I want to change this so that it goes slightly more aligned with the other. So I'm going to try to find, and this is a complete hack, but I'm going to try to find something that I can multiply here that will be good enough so that it decays as fast as the other one. So maybe if I multiply by 4 is too much, and just multiplying by 4 for no good reason, just because I found this somewhere in some other plugin, is a terrible idea. Oh yeah, when I multiply by 4, the RMS optimize seems to be going crazy. But if I do a full compile reset, then it works again. I don't know. It seems like 4 is too much. It is moving too fast. So instead, I'm going to multiply by 2. Maybe that will make it. Hello. Yeah, not good enough. Anyway, and what happens if I change the window size? Yeah, this one, oh, I probably should do a full compile reset as well. Now this one it is moving along. It's not perfect. Yeah, and if I cannot make it perfect, then I'll just, you know what, I forget about it. I won't try to make it good. This is an approximation. It's not a good one. Don't really like it, but it's faster, and I didn't have to keep a window. So that's good. Maybe if you're doing some kind of compression, and maybe you just won't care about this. I don't know. And that's all I have for you today. In the next video, and yes, there is still one more video. In the next video, we are going to look at a problem that we have been glossing over this whole time. The problem of how to deal with multi-channel. And specifically, in this case, we have a stereo track, but we could have a track with 6 channels. 10 channels. How do you compute the RMS of all the channels combined? It's not as simple as you may think. I mean, it's not rocket science, but there is a wrinkle and you have to know how to do it. And in fact, the original implementation of the auto mixer did it wrong. And when I learned all about this, I went there and I contributed back and I fixed it. But I will explain everything that is going on there. I see you on the next video. Thanks for watching this one. Make sure you subscribe to this channel so that you get notifications and everything for when I publish new videos about programming, about audio effects, about Reaper, and other fun stuff. Thanks for watching. I see you on the next one. Bye.